Right now, beyond the last planets, beyond the region where sunlight still feels powerful, and beyond the invisible shield created by the sun, Voyager 1 is moving through a place no human-made machine had ever touched before it. For years, the spacecraft has been sending back measurements from the other side of the Heliopause, the boundary where the solar wind finally gives way to interstellar space. Some of those measurements look so strange that scientists could not immediately explain them. A sudden increase in magnetic strength appeared where the environment was expected to stay calm. Then came a broad, sustained hump in the data. After that, the magnetic field remained unusually strong for years, refusing to settle back down. The signal was real. Its cause, for a long time, was not. Now, a new analysis has brought those old measurements back into focus. Researchers combining Voyager 1's observations with a large computer model of how the solar wind interacts with interstellar space have shown that the strange magnetic structure can be reproduced almost exactly by enormous, slow-moving compressions generated by the sun's own activity. These disturbances traveled outward from the sun, struck the Heliopause years later, and kept moving straight through it into the local interstellar medium. The boundary did not erase the sun's influence when Voyager 1 crossed it. It transformed that influence into something new and let it keep traveling. Voyager 1 had been recording the evidence all along. Scientists simply did not yet have the tools to read it correctly. This is not a story about an alien object, a hidden planet, or a secret transmission. It matters more than that because it changes how we understand the edge of our own solar system. For decades, the Heliopause was described almost like a clean, drawn border. Solar material on one side, interstellar material on the other. The new picture is messier and far more interesting. The Heliopause is not a solid wall. It is a moving, breathing interface where pressure waves, magnetic fields, plasma, and the sun's own 11-year activity cycle all collide and leave lasting marks on each other. What happens deep inside the heliosphere can leave fingerprints far beyond it, on the other side of a boundary most people assume should block everything the sun ever does. And that is the real meaning behind Voyager 1 was right all along. To understand the discovery properly, we need to go back to August 2012. Voyager 1 was roughly 121 astronomical units from the sun when its instruments recorded a dramatic, unmistakable change. Low-energy particles from inside the heliosphere suddenly dropped away, while high-energy cosmic rays arriving from the wider galaxy spiked upward. Plasma density around the spacecraft rose sharply at the same time. Voyager 1 had crossed the Heliopause and entered interstellar space, becoming the first human-made object in history to do so. NASA still describes Voyager 1 and Voyager 2 as the only two spacecraft ever to operate outside the heliosphere, but the crossing was never as clean as expected. Scientists had assumed the direction of the magnetic field would rotate dramatically the moment Voyager 1 left the sun's magnetic environment, since the two regions were expected to have very different orientations. Instead, the field's direction stayed surprisingly similar on both sides. That single detail delayed final confirmation for months and inspired competing explanations, before the particle and plasma data eventually became overwhelming enough that NASA formally confirmed the crossing. The experience taught scientists early on that the Heliopause was not going to behave like a tidy textbook border. Voyager 1 kept moving outward. Its cameras had already been switched off decades earlier to save power, so there would be no dramatic photographs of the darkness beyond the sun's reach. Every discovery from this point forward would arrive instead as numbers, waveforms, particle counts, and magnetic field readings, each one a message from a region of space that had never once been sampled directly before. To understand why any of this matters, it helps to understand what the heliosphere actually is. The sun constantly releases a stream of charged particles called the solar wind, which expands outward into an enormous bubble surrounding every planet and reaching far beyond Neptune's orbit. The outer edge of that bubble is the Heliopause. Beyond it lies the very local interstellar medium, the thin plasma and magnetic environment through which our solar system is quietly drifting. Calling that region empty space is misleading. Its density is extraordinarily low compared to anything on Earth, but it still contains charged particles, neutral atoms, cosmic rays, dust, magnetic fields, turbulence, shocks, and slow-moving pressure fronts. Over distances measured in billions of miles, even tiny changes eventually become significant. Voyager 1 began proving this almost immediately after crossing the boundary. In 2013, its plasma wave instrument detected oscillations triggered by a disturbance that had started much closer to the sun, letting scientists estimate the plasma density around the spacecraft with real precision for the first time, and confirming independently that Voyager 1 truly was beyond the heliosphere. More importantly, it proved something nobody had directly shown before. Disturbances born near the sun really could travel all the way out to interstellar space and physically shake the plasma beyond the Heliopause. The edge of our solar system behaves less like a solid wall and more like a shoreline between two oceans. The waters on either side remain genuinely different, yet a wave beginning on one side can still disturb the other. Then, beginning around 2017, Voyager 1 detected something even more valuable, a faint, nearly continuous plasma wave emission running quietly in the background. Scientists often call it an interstellar hum, though it is worth being precise. It is not sound traveling through air, and human ears could never hear it directly. It is an electromagnetic signature tied to natural oscillations in the surrounding plasma. NASA reported that this weak signal became clearly visible in Voyager 1's data around mid-2017, finally giving researchers their longest continuous map yet of interstellar plasma density. Because the signal persisted, rather than appearing only during rare, dramatic events, scientists could track electron density in something close to real time, instead of waiting years for the next major shockwave. That tracking revealed that interstellar plasma near our solar system is not remotely uniform. It contains fluctuations in hidden structure, with density rising by roughly an order of magnitude within a few years after the crossing, before settling into a broadly similar range with ongoing variations. Then came the most puzzling event of all. Around the middle of 2020, with Voyager 1 approximately 149 astronomical units from the Sun, its magnetometer recorded a sudden, sharp jump in magnetic field strength. The increase was followed by a distinct, sustained hump, and then by a field that simply refused to fully relax back down, persisting for roughly a year and a half, an unusually long stretch for a single feature that far beyond the solar system. Scientists needed a real explanation, and at first there were several competing possibilities. A local interstellar structure, Voyager 1, happened to cross by chance, a shock or pressure front from solar activity years earlier, only now catching up, leftover turbulence near the Heliopause, or a sign that scientists had misunderstood how quickly conditions should smooth out with distance. Because only two spacecraft in history have ever crossed the Heliopause, researchers did not have a fleet of probes to compare notes from multiple directions. They had Voyager 1, Voyager 2, decades of solar wind records, and physics. The new analysis combined years of Voyager measurements with a self-consistent magneto-hydrodynamic model, or MHD, which treats electrically charged gas and magnetic fields as one connected physical system, letting scientists simulate how the solar wind expands, how the heliosphere responds to solar activity, and what happens when pressure fronts finally reach the heliopause and push into interstellar plasma. Built using real solar wind measurements and the well-documented rhythm of the roughly 11-year solar cycle, the model was asked a direct question. Could activity tied to solar cycle 24 realistically produce the magnetic jump, hump, and sustained strong field that Voyager 1 actually measured years later and billions of miles away? The answer was yes. The simulations reproduced the essential shape of the puzzling data, almost feature for feature. Large, slow, global compressions tied to shifts in solar activity traveled outward through the heliosphere over years. When they struck the heliopause, the boundary did not absorb or erase them the way a rigid wall might. It transmitted that pressure directly into the interstellar medium, compressing the plasma and strengthening the magnetic field precisely along Voyager 1's path. What had looked like an unexplained structure beyond the edge of the solar system turned out to be a delayed echo of the Sun's own changing activity, arriving late, but arriving clearly once researchers had the right model to recognize it. That is the real, scientifically grounded meaning behind Voyager 1 was right all along. The spacecraft was never malfunctioning. The hump was never meaningless noise. Voyager 1 had recorded a real physical response to solar pressure that had traveled all the way beyond the heliopause to reach it. This discovery changes the mental image most people carry of the heliosphere. Instead of a static bubble with one fixed edge, picture a vast magnetic cavity that expands and contracts, rhythmically responding to the Sun's 11-year cycle. As the Sun grows more active, then quieter, the speed, density, pressure, and magnetic strength of the solar wind all shift in response. Those changes ripple outward, but because the heliosphere is so enormous, the effects can take years to reach its boundary. When they arrive, they can deform the heliopause, compress the surrounding plasma, and send fresh disturbances rippling beyond it, producing something close to delayed space weather, playing out light days from where it began. Events tied to one phase of the solar cycle can show up in Voyager 1's data years later after traveling well over 100 times the distance between Earth and the Sun. By the time Voyager 1 measures the disturbance, the conditions that created it may already belong to an earlier, mostly forgotten chapter of solar history. That built-in delay is a large part of why this mystery was so difficult to solve. Scientists could not glance at what the Sun was doing in 2020 and connect it directly to that year's magnetic hump. They had to reconstruct the journey of solar wind structures across many previous years, account for a shifting heliosphere, model the interaction at the boundary, and only then compare the prediction against reality. The analysis also found that magnetic compressibility remains present much farther beyond the heliopause than a simpler model would predict, with Voyager 1 detecting time-dependent variations out to roughly 165 astronomical units. That means Voyager 1 is not moving through perfectly untouched, purely galactic interstellar space. It is traveling through the very local interstellar medium, a region still measurably influenced by its proximity to our heliosphere. People often hear that Voyager 1 has left the solar system, and imagine it has escaped everything connected to the Sun. In reality, the solar system has several different boundaries. Voyager 1 crossed the heliopause, the edge of the solar wind's bubble, but it remains deep inside the far larger region, still shaped by the Sun's gravity, nowhere near the distant Oort cloud. Even beyond the heliopause, it can still encounter disturbances that began as ordinary solar activity, simply delayed by years of outward travel. None of this means the heliopause is imaginary. It means the boundary transfers energy in more complicated ways than a rigid wall ever could. Picture a drum skin stretched between two rooms. Air does not pass through it, yet a strike on one side still produces a wave felt on the other. The physics differs in detail, but the idea holds. A boundary can separate two environments while still transmitting energy between them. Voyager 1's magnetometer turned out to be uniquely suited to detecting exactly this kind of effect, sampling the local magnetic field directly, rather than inferring it from Earth. Its plasma wave subsystem supplies the other half of the picture, estimating electron density well enough that, together, the two instruments can reveal whether a structure is a density enhancement, a shock, a pressure front, turbulence, or a broader magnetic compression. These have effectively become Voyager 1's remaining senses, in a region where an ordinary camera would show little more than scattered stars. This is why keeping Voyager 1 operational remains so valuable even after nearly 50 years. As of 2026, only two of its original science instruments remain active, the magnetometer and the plasma wave subsystem. NASA has steadily shut down other systems to conserve power as the spacecraft's radioisotope generators weaken by roughly 4 watts every year, including the low-energy charged particle instrument in April 2026. The two instruments still running happen to be exactly the ones needed to keep studying magnetic compressions beyond the heliopause. The spacecraft is old. The science it makes possible is not. The new model also offers a genuinely testable prediction. Major solar-driven disturbances tend to decelerate with distance, making it unlikely Voyager 1 will be overtaken by the main solar cycle 25 disturbance. Voyager 2, traveling through a different region of the Heliosphere, is expected to encounter its own distinct compressions instead, including at least 2 events before the end of 2026, and possibly a major solar cycle 25 disturbance similar to what Voyager 1 experienced, arriving sometime around the end of the decade. If the field near Voyager 1 evolves as predicted, and Voyager 2 detects the expected compressions along its own trajectory, confidence in the model will grow. If not, the model will need revising. Either outcome moves the science forward, because the two Voyagers remain the only source of measurements like this anywhere. There is a larger consequence, too. The heliosphere shapes the radiation environment of our solar system, and data from both probes helped confirm that it shields the inner solar system from a majority of the surrounding galactic cosmic ray radiation that would otherwise reach it. If solar cycle compressions can move straight through the heliopause, they may also influence particle transport, turbulence, and magnetic conditions well outside the bubble. None of this poses any immediate threat to Earth, since by the time these disturbances reach Voyager 1, they are already billions of miles away and weakened. But they reveal how deeply connected the heliosphere remains to the interstellar environment surrounding it. This finding also reshapes how scientists think about future missions. Voyager 1 and 2 were built to explore the outer planets, not to serve as dedicated interstellar observatories, and it shows. Voyager 1's direct plasma instrument stopped working long before the heliopause crossing, forcing researchers to infer density indirectly through its wave instrument instead. A dedicated future mission could carry modern sensors built specifically to measure plasma, neutral atoms, cosmic rays, dust, magnetic fields, and turbulence across the entire boundary at once, traveling faster and sampling in far greater detail. Voyager 2 provides a genuine second path. Across the heliopause in November 2018, through a different hemisphere, still carrying a partially functioning plasma instrument Voyager 1 no longer has. That let scientists compare the two crossings directly for the first time, and the boundary looked meaningfully different in both places, proving the heliosphere is not a perfectly symmetrical bubble. Voyager 2 also confirmed Voyager 1's surprising result. The magnetic field beyond the heliopause remained broadly aligned with the field just inside it. With only one data point, scientists could never be sure that wasn't a coincidence. With 2, the pattern held. Together, the two spacecraft reveal a heliosphere that is uneven, variable, and constantly responsive rather than fixed and symmetrical. It breathes in rhythm with solar activity. Its boundary physically moves. Pressure fronts strike it, and shocks pass through it. And the space immediately beyond it appears to remember events that began much closer to the sun, sometimes years earlier. That is the deeper discovery hiding beyond the heliopause: memory. The interstellar medium closest to our solar system carries a delayed record of past solar activity, and Voyager 1 has been reading that record one magnetic structure at a time, without originally realizing what it was doing. That connection is easy to underestimate, because almost nothing about it happens quickly. A solar eruption near Earth can disrupt satellites within days. The larger pattern of an entire solar cycle can take years to produce a recognizable compression at Voyager 1. The signal arrives long after its cause, and scientists are left reconstructing that history backward, years after the fact. Real uncertainties remain. Models like this depend on assumptions about the solar wind, the heliosphere's shape, the interstellar magnetic field, and how turbulence behaves, and Voyager 1 only follows one narrow path, through an enormous three-dimensional environment. A successful simulation is persuasive evidence, not automatically the final word. Scientists will keep testing this model against new data from both spacecraft for years to come, and that caution makes the discovery stronger, not weaker. It is a genuinely testable explanation, one that makes specific predictions about what comes next, rather than a final verdict that closes the book on this region of space forever. Meanwhile, Voyager 1 continues moving steadily outward. On November 18, 2026, it is expected to become the first human-made object ever to sit a full light day from Earth, roughly 16 billion miles away. At that distance, a single radio command needs a full 24 hours just to reach the spacecraft, and any response needs another 24 hours to return, making a complete round-trip conversation take roughly 2 full days. The distance is astonishing, but the deeper achievement is quieter. A machine designed in the 1970s, with barely more memory between its computers than a pocket calculator, is still testing a brand new 2026 model of plasma turbulence and magnetic compression far beyond the heliopause. Its power is fading, its signal grows weaker every year, and its remaining instruments are being switched off one by one as necessary. Yet its measurements remain irreplaceable, simply because no newer spacecraft has ever reached its location. That is Voyager 1's real legacy. It did not merely visit Jupiter and Saturn and quietly retire. It became the first human-made instrument to enter interstellar space. It revealed that the heliopause was far more complex than expected, detected plasma oscillations, and a persistent interstellar hum beyond the boundary, and measured a mysterious magnetic jump and hump that puzzled scientists for years, until those very measurements were shown to fit a much larger story about the sun quietly sending pressure out into the space between the stars. Few instruments built nearly 50 years ago ever get the chance to prove themselves right decades after the fact. Using data nobody had the tools to properly interpret at the time it was first recorded. So when people say NASA found something beyond the heliopause, they are not describing some solid object waiting in the dark. They are describing a hidden connection. The sun's influence does not end with a clean cut at the heliopause. Changes in solar wind pressure can reach that boundary, disturb the nearby plasma, and leave magnetic structures that persist for years. Voyager once recorded that connection, long before scientists fully understood what they were looking at. The spacecraft did what great explorers have always done. It reached a place where the old map ended, measured something that refused to fit the expected picture, and quietly waited for human understanding to catch up. Now, the picture is becoming clearer. The heliopause is not a dead, static border. It is an active, living interface. Interstellar space near our solar system is not perfectly calm and empty. It carries shocks, compressions, turbulence, plasma oscillations, and the slow, delayed rhythm of the sun's own activity cycle. And somewhere out there right now, more than 15 billion miles from Earth, Voyager 1 is still listening quietly to that ongoing interaction. Its instruments are aging, its power is disappearing, and one day its signal will finally stop. But until that day arrives, every new measurement it sends home can help test the prediction, refine the model, and reveal one more piece of a boundary humanity has only just begun to explore. The universe beyond the heliopause is not silent. It is carrying the echo of our own sun. And Voyager 1 heard it first. If you want more real discoveries from the true edges of what science actually understands about our solar system, subscribe and stay with us. Because the farther humanity travels, the more the universe keeps forcing us to rewrite what we thought we already knew.